Going from Setfos 5.5 to 6.0 means that there are quite a few features new in Setfos 6.0. For those of you who haven't seen yet the new Setfos, that's how Setfos 5.5 looked. And besides many new features, the developers did also a very good job in changing the user interface. So you can see here now the same file opened up in the new Setfos 6.0. Let me now introduce you some of the new models which are in Setfos 6.0. I will not go through all of them, but I want to mention one other model which is inside because it also relates to degradation of perovskite, which is the tunneling model, and one important factor in degradation of perovskite is also reverse bias, specifically when going towards thinking about module application where you have shading of a cell, which leads to reverse bias of solar cells. So to understand this breakdown, as you can see here on the bottom left of a solar cell, we looked into this in a project with a recent publication of a colleague of mine. You need to understand the tunneling, or you need to have a tunneling model inside to get this breakdown, which is partly due to strong fields you have then at the interface, which means they are also influenced, as you can see here in this graph, by ion density, which modifies the electric field. So first I will introduce the degradation model, and it's even labeled here OLED degradation model, since big part of introducing this model is coming from the OLED field. You can also apply it to solar cell, to perovskite, but I will show now the OLED side. Well, first, for those of you who are not familiar with OLEDs, from a solar cell perspective, with respect to recombination, what you care about is just decreasing recombination as much as possible. Get rid of dark Schockler-Rittal recombination. You can't get rid of the radiative recombination, but essentially in the solar cell, at first approximation, you don't care about it. But in OLED, the story continues, because what you care about is an exciton that forms if you have radiative recombination. And this exciton, this is a charge pair which is not separated. In the end, leads to a radiative recombination, but it can also be quenched. It can transfer its energy, and then it's lost, so to say. It cannot recombine radiatively anymore. And this quenching here of these excitons, that's what we find in OLED literature, leads to generation of trap sites, which in turn then increase again Schockler-Rittal recombination. So you see here that's already quite a complex system for which simulation and modeling is then a good tool to look into it. So you find in OLED literature different ways of how to model, and that's what this field cares mostly about. It, like in solar cells, the maximum power point tracking with time. You have here the luminance decay at a constant current, and you can see here several examples of how different models, either analytical or also a full drift diffusion model, were applied to understand this degradation in OLEDs. And the core of these models is the evolution of the trap or quencher concentration with time, and also laterally or through the device, with which results of different processes. You can see here it can either be, you can either have just a simple trap site generation from the whole profile or electron, but what's mostly looked into in OLEDs is this Exciton-polaron quenching, where the exciton is quenched due to the hole density. So I show you an example in Setfos, where we have conveniently already a model in the, or a tutorial file. So if I look into the OLED files, I open here the degradation example. So for those of you who are not familiar with Setfos, I just quickly introduce the user interface. So you have here next to the files which I open now, you have here the definition of the stack. So here you could add another layer, for example, which we don't need at the moment. And then for each of these layers, you define your parameters in first base. That's the optical parameters here for the emission layer with refractive index, real and imaginary for absorption. And then, of course, also for drift diffusion, you define your parameters for the charges and, for example, also the charge mobility, which you can see here is in OLEDs often field dependent. You define your excitons or your exciton, your one exciton in this case of this example. And importantly now, you can define your trap here. So we have one trap defined, and you can here put in the trap energy. Conveniently in the energy level section here, you can see also where your trap is situated according to the parameters you set. You have here capture rates. So at the moment there is a model based on the parameters we put into the model defined, but what you often find is also a constant capture rate. And lastly, here is the degradation model where you can choose which events lead to trap site. And what you see here is what's defined is Exciton-polaron quenching for holes. So if we look into this equation here, that's just the light blue part, which is now generating trap sites, quencher concentration with time. So we can run this model or this file here and play around with it. So the first thing we could do while this is running, I turn off the degradation model to see how this looks like in comparison. So the files are generated here on the side and we can compare it later. And what I also do now as a comparison, I turn off the Shockley-Rittal recombination. I will explain in a second what this means. What I'm doing is I'm setting here the electron capture rate to 0. So what I did now, just to show you this, is in the Shockley-Rittal model, I turned off here the electron capture rate, but what's still going on is that holes are still trapped. So you still get the hole trap density, and this hole trap density also influences the whole system. So we can have a look at how these different simulations now look like. So in first case, if we look directly at luminance transient with the degradation model disabled, you see here with time there is no change in luminance. If we have this trap site which evolves, there is a big change in luminance with time. And if we turn off the Shockley-Rittal recombination, you still see a decline of luminance. Now, to understand this, we could look into the model, what's going on. We see that less traps are, or a different amount of traps are generated, and you could, if you would want to look deeper into the different profiles of charge densities to understand what's going on here. Last interesting change is, of course, you can have a look at different models of what effects or factors are leading to trap site. So instead of hole polaron, I choose now electron in combination with excitons to lead to trap states, and to kind of have a look at how then the luminance curves looks compared to the whole exciton or polaron exciton quenching. And you see that now with choosing electrons as a quencher, nearly nothing happens. So this looks surprising. So we could look into the model, what's going on here, and see that, okay, in the model we had here, there is quite a low electron density compared to the hole density. So in turn, also you don't generate much traps because of that. And you could look further into that. But I will go on now with the thermal model, which can also be used for solar cells and OLEDs. Again, I start with the OLED side to show the different aspects of the thermal module, or the different thermal models. So the first important one specifically for OLEDs is Joule heating, which is essentially resistive heating. So you drive a current through a resistor with an applied voltage, which leads to heating. And this Joule heating, if you go in OLEDs to larger current densities, you can see here, leads then to quite strange effects, because the heating itself then influences the electronic parameters, and you can get quite some peculiar shapes here, which you can model. But even before this effect, if I go to lower voltages, where the current starts to rise slightly, you see these changes already in impedance spectroscopy features, for example, as another low frequency features you can see here. To model this, you need this self-heating, you need Joule heating. That's the first aspect of the thermal model. Second one is heat lost or heat generated because of recombination losses. So everywhere where you see here this flame, that's where heat is generated, either here in a dark Shockley Hall recombination, the energy gets transferred to heat. Also, if excitons are quenched, the energy can also get transferred to heat. So you need to consider this in a full model. And the last element I'm talking about now, back again to solar cells, is the optical heating. So the thermalization, if you absorb a photon with a higher energy than the band gap, then the energy of the electron, which gets dissipated while going down towards the band gap, that's lost in heat again. So to look into this, I set up a quick model. It's not the full Shockley-Queisser model in Setfos here, because we still have optical losses, as I was modeling the optic part still with a realistic refractive index. But you get the same trend here with the model when shifting the band gap of the perovskite here, as you can see, for the power conversion efficiency. You can look at the non-absorbed photons which are not absorbed. So the dark green here is transmitted photons through the device which are not absorbed. So you see here there's still some reflection. That's not part of the Shockley-Queisser model, for example. But what we can do now is look at this thermalization part in more detail. So here you can see the same trend where you have higher thermalization the lower the band gap is, because more bigger part of photons that are absorbed are lost in heat, so to say. So we can go into back into the model again and look at this file in more detail. So what I set up here is to go towards the Shockley-Queisser limit. It's just one absorber, and you see here that the injection is perfect level. There are no injection barriers. As I said, I still have a model here, an optical model. So what we're looking at now in the results is directly at the generated power, where we now can split up the heating we saw before and look into the different factors. Now in this simple model, the biggest part, or in general the biggest part, is the thermalization. But even in the simple model with no recombination heating, for example, we see there is this Joule heating, which you cannot avoid, as you need to extract the charges, so there will be some fields, some voltage loss and current, so you will have Joule heating, and that's part also of the Shockley-Queisser model. Now it looks like that this Joule heating is like it's not dominating. It's the whole situation is dominated by the optical heating, by the thermalization. But if we go towards higher bandgap, you can see here that these two factors getting closer. So if we have a look at again full model at a higher bandgap of 1.6 eV. So you see here again with the transport layer simulated and injection barriers, along with some Shockley-Ritol recombination. If we look at the results of this simulation, you can see here that the power that is lost in heat, the heating power, has quite a peculiar shape when looking at just looking through the swept voltage from JSC short circuit towards VOC, and that's because the Joule heating is getting comparable to the thermalization. And just to understand this curve better, if we look at the device current here, the simulated one, if we go from maximum power point here towards short circuit, for example, you extract less and less energy. So if we look at the electrical power with the maximum power point here, if you are at short circuit or at VOC, you don't extract any energy anymore, which means in turn that this energy must be again dissipated in heat. And what's important now is to understand how this heating power is translating to actual cell temperature. So in the model I chose here, you can see that this power translates only to a minor temperature increase here from 300 Kelvin was chosen as rough room temperature environment. But that's because, and now we are looking into some of the parameters of the thermal model, that's because if we go to the boundary condition, which is set up as a convective boundary, so you have airflow, for example, this parameter here, the transfer coefficient of 100 watts per square meter and per Kelvin, represents a very strong airflow. So if we want to have a look into how the temperature changes if we go set a parameter which represents no airflow at all on both sides, then we can run this example, and I have to put here the voltage sweep to only 1.1 volt, otherwise the simulation takes some minutes, which we can't do now in the live view. So with nearly no airflow, you can see here that the temperature effect is now quite drastically compared to the case if we have very strong airflow. So with this model, you can look into this. You could now look into what's happening if we go towards 85 degrees. Of course, you see here there's both air on both sides. If you measure a device, typically you would have on one side a direct contact, so this changes the situation. But this situation would be representative for if you would put a device on contacts and it's somehow surrounded by air, not laying directly on the heating plate, for example, or some other material. So there is more to this story of a thermal model, but I will not go through all of it. I just want to mention here that the model also considers Thomson, Peltier, and Seebeck effects, which are for certain devices very relevant, but as it turns out, these are also relevant to model. It's not dominating, but model part of the heat that is generated in solar cells and OLEDs as well. So you can find more information on these models if you're interested on the web page here, and you can always request a free evaluation license